Alright, let's do this. It's not perfect. It's not. Wait, okay, there we go. So, this is going to be the problem for the capacitance that I'm going to do for the extra points. We're going to do A first off. What is the equivalent capacitance of CEQ in the array? So, this whole thing. Alright. Okay. Since these are capacitors, what we're going to do is first off combine both of these and both of these, and then we're going to do like a whole combination again. So first off, the capacitance of C3 and C4, because of the fact that they are in parallel, means that it's going to be C3 plus C4 equals 77 UF. Alright. And for C1, C2, C3, 4. And for C1, 2 equals C1 plus C2 equals, it's gonna be 10 plus 11.3, so 21.3 UF. Alright, after this, these two have been calculated. Essentially, now what we have is a circuit of this, like that. And we have two capacitors in series with these capacitances. So what we're gonna do now is do C1, 2, 3, 4 equals 1 over 77 plus 1 over 21.3 to the minus 1. That is going to be equal to 16.68 UF. And this we are going to round up to 3 significant figures, so 16.7 UF. Alright. After that, that is A. A is finished. What is the charge stored in CEQ? The formula for charge is, if I remember correctly, C equals Q over V. Therefore, CV equals Q. And right now, we have 10 volts of energy. So we're going to do 16.7 times 10 equals 167 charge coulombs. Wait. Yeah, wait, no. It's, yeah, okay, wait, hold up, wait a minute. 10 times 10 to the minus 6 times 10. There we go, because here it's microcoulombs, and we have to account for that, which is going to be equal to 0.000167, or alternatively 1.67 times 10 to the minus 4. There we go. Okay. Now, a dielectric with K 2.5 is inserted between the plates. What is the charge? The dielectric is essentially just a multiplier. So what we're going to do here, wait, I'm going to divide these. So what we're going to do now is just take what we just got and multiply it by 2. 1.67 times 10 to the minus 4 times 2.5 equals 0.0004175 coulombs, or alternatively, again, 4.18, because we're rounding in up to 3 significant figures, times 10. Why is it? I'm always doing to the minus 4. It's always like in this, it always does this. I don't know why. Let me spin it just a bit. Wait. Alright. There we go. That's that. Okay, so now we have the charge after the dielectric is inserted. Now suppose the capacitor is disconnected from the battery and isolated. If we now remove the dielectric, what is the charge and potential difference of the isolated capacitor? Wait. Oh wait, no, actually this is not, this is status 7. Okay. Once that's done, the battery is disconnected and we remove the dielectric. Okay. So because of the fact that this is essentially Thanos snapped from existence, wait, actually I'm gonna delete it here because this is 2 capacitors. Essentially, because of the fact that this is Thanos snapped from existence and the capacitor stays alone, the charge has nowhere to go. It will stay at the constant 4.17 times 10 to the minus 4. It will stay at the constant that. But what does change is the voltage. So now what happens is that the capacitance of this the capacitance is going to be the same. Wait. Okay, yeah. The voltage changed and the capacitance is going to go back because we removed the dielectric. So what we're going to do now is it's take this and divide it over 17.6, 16.7, sorry, 16.7 times 10 to the minus 6, and that is going to be equal to times 10 to the minus 4 over 16.7 times 10 to the minus 6. I don't know if you can see the flickering in my computer. I don't know why it's doing that. I'm sorry. It's really annoying for me. Okay. That is going to be 24.97. I think I'm going to round that up to 25. Yeah. 24.97. 7 point 97 volts, which is equal to essentially 25 volts. That's it. And last question. What's the energy stored in the isolated capacitor before and after removing the dielectric? Huh? Wait, what do you mean by that? Like each capacitor individually? I think. I think that's it. Okay, wait. The formula for... Okay, I think it's just gonna be the charge. We have the individual capacitance, so I think we can just take the charge. Wait, no, because the charge is not constant. Ah! I forgot! Okay. For these two, the charge is gonna be the same. It's going to be just... Okay, yeah. So for these two, the charge is going to be the same. So we take... Okay, the charge is going to be the same as the rest of the circuit. So, yeah, the charge in these two stay constant. I think. Wait. God. Okay, my bad, I'm back. I had to consult the ancient texts. So essentially, to see the energy stored, essentially U, what we're gonna do is take the formula 1 over 2 times the... Is it the... Yeah, the capacitance times the voltage squared. Alright, so before BF... Okay, before it will be equal to 1 over 2 times the capacitance times 2.5, because we have our special dielectric that is worth 2.5 times the voltage squared. And this will be equal to 1 over 2 times 16.7 times 10 to the minus 6 times 2.5 times the voltage squared, which in this case is going to be of 10 because it hasn't changed yet. So 10 squared, which is going to be equal to 0.0028. Sorry, I'm copying from my thing here because I don't want to use my calculator. It takes too long, but it's fine. I'm still doing it. 2856 20856 5 joules, or in other words, it's going to be 2.08 times 123 times 10 to the minus 3 joules, or in other words, 2.08 millijoules. MJ. That's for before. I'm gonna go ahead and just squish this. There we go. That's perfect. It's beautiful, isn't it? And it's completely readable still. It's fine. It's fine. It's fine. It's fine. There's no problem. And after the man behind the slaughter. Forget about it. It's a reference. Okay, it's 1 over 2 times the capacitance, and not the dielectric this time because it has been removed, times the voltage squared. So that's going to be 1 over 2 times 16.7 times 10 to the minus 6 times 25 squared. And that is going to be, I'm reading again, but it's fine, I'm still doing it. That is going to be equal to, I'm going to skip directly to the millijoules now, 5.21 millijoules. And that's it for our problem. That's one of two completed. Yay! I'll see you in the next one. What's up?